Okay, let's begin. So remember, we have our first test tomorrow. You guys been studying? Just a reminder, test 1 tomorrow. So it's 6 problems long. 4 computational. 2 proof-based. I think this has 70 of the points, and this has 30 of the points. So technically you can pass without knowing the proofs at this point, but that will change as we move on further, and it covers chapters 1 and 2. Alright, so everything before vector spaces. So we did chapters 1 and 2. We're skipping chapter 3, we're not going to do that, and now we're starting chapter 4 with vector spaces. So the first test is on chapter 1 and 2. I might throw in some, there'll be a bonus section as well, where you get any extra credit points. That might be on some items that we learned from vector spaces so far. And maybe a little bit beyond. So that's roughly going to be it. It's going to be the full time, 1 hour, 40 minutes. So we have the entire class time, and leave whenever you're done. Any questions about that? So basically chapter 1 and 2 stuff, know how to solve systems, know Cramer's rule, know how to find inverses, determinants, how to use them, things of that sort. Know how to do proofs. So the proof problems, there are 2 different types. So in one of the proof problems, it'll have like many parts where there are many little mini proofs that you do, that it's easy to justify them in like 1 line or 2 lines or so. And then there's another problem where I think I put 2 parts in it, but where they're just a bit larger kind of proof, where you have to examine, where you have to write out more sentences basically. But that's basically it. So continue chapter 4. So we're in 4.2 so far, but just a reminder, so we can say V is a vector space over F is implied with respect to the operations plus times if one V non-empty is a set, no restrictions on what this set could be or what its members could look like. F is a field. 3 with 2 operations. Which we call addition and scalar multiplication. The set V, we call its elements vectors. The set F, we call its elements scalars. Addition is an operation that combines 2 vectors and creates a 3rd vector. Scalar multiplication is a rule that combines a scalar and a vector to form another vector. And for the operations obey the 10 rules. There are 10 vector space axioms. And it must obey these rules. And I might be sloppy, so I'll just mention that from now on. If I say something like V is a vector space, then I just move on and start saying stuff, it is tacitly assumed that all these things are in place in the background. There is some field that is in consideration. There are operations that are in consideration. I'm just not taking the time to mention them. So it is sloppy for me to just say the set is a vector space, because there's really a bunch of things that have to come together to create a vector space. But sometimes I'll just say, let V be a vector space, and then I'll say some theorem, but it's assumed that all these things are in the background. Yes?
Did you mean to write that V is not equal to the empty set?
Not the empty set. Right? It will be assumed that there are some F operations and they fulfill the properties. And that'll be usual. So any time you're reading in a book where it says, oh, if this is a vector space, then blah, it means there's a lot of things going on in the background, but they're not mentioning it, and that's because it would be understood, or should be understood, that once they mention something is a vector space, they're automatically mentioned for things coming together. We also moved on to the idea of a subspace. So U is a subspace of V if U is a subset of V and U is a vector space with respect to the same field and the same operations. And we have a very important theorem, so this is something you should know. U is a subspace of V. That will be true if and only if, one, U is closed under scale, closed under addition, and two, U is closed under scalar multiplication. So far, these are some facts that we know about vector spaces. Just want to, you should always keep these in the background. They're very important ideas. So vector spaces can be large, but knowing that we're in a vector space, sometimes we want to study subsets of this vector space, and we want to know, do our vector space rules work on those subsets? And we only have to verify 2 elements of the axiom instead of all 10, because these 2 will imply other 2, and then the remaining 6 we get kind of for free, right? So it'll automatically be the case that, for example, that U1 plus U2 is equal to U2 plus U1, right? Because, so if I know that U1, U2 are in U, then this will be true because U is a subset of V. So these guys are in U automatically means they're in V, and in V this works. So we can get some properties for free. But these 2 properties help us to get the negatives and help us to get the 0 vector, and those are the 2 properties that we wouldn't get for free. So that's important. So we'll do some more examples now, and then get into some new material, I think. Continue with something where I did that already. I gave an example of the 0 subspace, invertible matrices. These are non-example symmetric matrices. Here's an example. Question, vector space or not? Okay, so I'm going to define some detail. So U is a subset of R2, and U is the set of all elements in R2 that have this form. Or x squared plus 1 such that this is in R. Right, so these are elements in R2, so we can think of them as vectors. And that's the form. And yeah, subspace or not. Technically I want to say subspace, but saying it's a subspace is saying it's a vector space just within a larger vector space. So let's check the two properties. One, how would I check closure under addition? How do I go about doing that?
I have a question.
Yeah.
Why don't you need to check that the zero vector is also in the subspace? Is that covered by the closure and the
That's
multiplication?
covered by scalar
If
multiplication.
you can-
Because the scalar 0 will
Oh,
give me
okay.
the zero vector by the theorem that we had.
Okay,
So the zero vector is definitely going to be in there.
okay.
Take two vectors, label them a different variable, and then
Okay,
add them.
so let, what do you want to call the two vectors? U1 and U2 be in U. Then, how can I describe them? Oh, and by the way, we're talking about the usual vector operations. Here. The ones you know from Calc 3. Yeah, so how would I describe them and verify?
Should we label like x?
How do I know if I add these two things, I get something in the set or not?
If you can write it in that form.
Like that, yeah.
Okay, so what does that mean I should do here?
Well, each vector individually will take that form.
Right, so,
I'm just trying to think of what a variable. Do we use any one?
X
of one.
Oh, okay.
A squared plus 1,
Oh,
let U2 equals B squared plus 1. These are definitely members of that set, they definitely look like that. And if we take U1 plus U2 in this case, this will give us, with the usual vector operations, A plus B, comma, A squared plus B squared plus 2. Does that work?
Yes.
Just like,
No.
yes, no.
The last part isn't in that form, right?
Well, how do you know for sure? What should be the form? Like here, maybe I should do that. So this is
Split it up.
also from the 308 class. If you're never sure how to answer a question, it means you probably don't know where you should end up. So let's look at what it should look like. The form says this, right? Now the idea is, if I don't have x here, I could have something else. That still needs to fit. Which means if I put an a plus b here, it should be the same as putting the a plus b here in order to fit that form. Now an a plus b being there means that's a squared plus 2ab plus b squared plus 1. Right? So that is clearly not the thing that I should be getting. This is not a squared plus 2ab plus b squared plus 1. And so what can you say? It's not a vector space. It's U is not closed under addition. Which means U is not it's not a vector space, which means in particular it's not a subspace of R2. Now this is going to be typical. There, a lot of times, and I'll definitely ask you to do this in future tests, and you'll see it in future homeworks. We're going to describe some subset of some larger set that we know, and a lot of the times we'll happen to know that it's a vector space. So if we want to verify some subset as a vector space, it's very important that we pay attention to the form that things are in. So they're going to describe to you exactly what is the criteria that puts you in this subset. And you need to verify with that criteria whether things will work out or not. So you have to say, if things are in this form, if I add two things of this form, it will give me back something of that form. That's the kind of thing that you're verifying. So while the two conditions you're checking are always the same two conditions, how it looks to check that, the actual details can vary greatly depending on the kind of objects you're looking at. So if I was talking about some sort of matrices, you would have to verify how things look with matrices. So for example, I could say, if U is the subset of N2, we actually looked at this, right? Where, I don't remember, did we do the details here? U is the set of 2 by 2 symmetric matrices. Did we do this or no? Let's actually do it now, because I don't remember writing it out, but for
Oh, you
this
wrote it
class.
out, but we didn't have time.
Okay, so let's actually do it. So what can I say here? So if is U a subspace, is the question. Now we'll take it for granted that the set of all 2 by 2 matrices with usual matrix multiplication and matrix addition and scalar multiplication is a vector space. It will satisfy all the 10 properties. Okay, so now I'm saying let's take a subset of all those. Let's not look at all the 2 by 2 matrices. Let's look at the ones that are symmetric. Are they a subspace? What would my verification process look like? What would I need to verify? Well, at this point you should know we need to check the two properties. So let's check closure under addition. What would that look like?
So you have a 2 by 2 matrix A, B, B, C times another 2 by 2.
So let A, B, B, C.
Sure.
Sure.
Okay, and then comma, can I do another 2 by 2 symmetric matrix with some other?
Sorry, next one, like D.
Okay, D, E, E, F.
So assume these are elements of our sector U. Now, why did you not do this random thing?
Because that's not a symmetric.
Because it's not symmetric. You have to respect the form that we're telling you it is in, which means you need to be symmetrical about the main diagonal. Meaning if you're plugging in random variables that should be able to represent any arbitrary thing, you need to make sure your arrangement of the variables that you're using satisfy the property that we're describing here. Symmetric means we're symmetric about the main diagonal. So when you're writing out an arbitrary element of your set, you need to make sure it's symmetric about the main diagonal, is what I'm saying. Now you need to show that given these two elements, when I add them, I have an element with the same property. If I take A, B, B, C plus D, E, E, F, this would give me, by the usual matrix addition, A, D, B plus E, B plus E, C plus F. And you'll notice that all over this guy, it's symmetric. So this is also in U, and so we have the closure under addition. Let's look at the scalar multiplication. So let's check closure under scalar multiplication. So then, let A, B, B, C be in U and K a scalar. Then if I take K times this guy, A, B, B, C, that will give me KA, KB, KB, KC. Notice that if I check the main diagonal, I have the symmetry, so this is an element of U. This means, therefore, U is a subspace of M22. So the symmetric matrices form a subspace, right? And you do that by verifying the two properties. And notice, I'm verifying the same properties, but it looked very different doing it here as opposed to doing it there. And this is the kind of flexibility that you need to have. You can't assume any random thing. You have to make sure that the thing you're looking at fulfills the desired properties.
I have a quick question to clarify. M2 by 2 is just any 2 by 2 matrix, right?
Yeah, so
Okay.
so M2 by 2, or in general you can think of M by N, is just a set of all possible arrangements such that A, B, C, D are real numbers.
A quick question. So let's just say, whatever reason.
But then when I'm talking about U, I'm picking the ones out of this specifically
That are
where the
symmetric.
C value is equal to the B value.
Okay.
And that gives me this subset.
Okay.
And then, yeah.
Okay. Okay, so then just to be clear then, so for it to be about, I mean, so this just demonstrates that, okay, because it fulfills the properties of both symmetric and general matrices. Meaning to say, if that had produced KL or something, I mean, it would be part of the vector space of matrices, just not.
But not in this subset, which
Okay.
is a problem.
Okay.
Right. So, yeah.
Is there just infinitely many subspaces for 2 by 2 matrices?
Infinitely many subspaces? Well, yeah.
You just have to construct the operations, right?
Yeah, you just need to make sure you construct the operations that make it fit.
Okay.
And you can do something like, you can do some stupid things a lot of the times. Of course, in practice, you'd want to do something that's going to help you towards some goal you're doing, but I could just say, take the subset of all 2 by 2 matrices such that the components are 1 plus a real number. You can literally write anything. Okay, so it's 2 plus a real number. 3 plus a real number. And you can do that forever. And all of these would form subspaces. They'd all actually be equal to M22. This is getting into isomorphisms is where we're going to talk about it. But you're going to realize that there are going to be times where it seems like you're creating different subspaces, but they all really are the same. It's kind of like you're just juggling guys around, but you're not really changing anything. And that idea is going to be, we'll look at much later. That's in chapter 8 when we'll look at that idea. So you'll hear math people say all sorts of crazy things sometimes. Like, kind of like what I said with the magic squares yesterday. I'm like, there's only one magic square that's 3 by 3. Well, technically you're gonna, I can find 3 of them. But no, they're all the same. You just flipped it in a mirror. It's the same thing, you know? So things can look different, but ultimately their essential properties make them exactly the same. So pretty much all the subspaces I just mentioned, they're all actually all of M22 itself. Right? So even though I randomly throw out some property, it turns out all those properties really point to the same guy. And that can happen. So on the surface you can have an infinite number of subspaces, but there are times when they all actually reduce to a finite case. And you won't always have an infinite number of subspaces. In fact, we're going to do examples where we don't have infinite subspaces. Let's look at that now. Example. Which, this would probably have been better if I jumped straight from the R2 example to this example. But let's just do this. Let's talk about subspaces of Rn. Now Rn, remember this is the set of all n coordinates of length n where the components can take on any real number. There are a lot of them, right? And you can do a lot of silly things to create subspaces. You can talk about all sorts of properties, but it turns out that no matter what property you give, you can only create a finite number of subspaces of Rn. If I'm taking these typical operations. So with the usual operations. Let's do the first few. Let's actually think about this. R. And I'm going to list the subspaces here. Let's actually try to exhaust them. Tell me some subspaces of R. I'm on the real line. R over R, give me a subspace.
Q.
Q. Is Q a subspace?
I think so.
What do you have to verify? You have to verify two properties. Is it closed under addition? If I add two rational numbers, do I get a rational number?
Yes.
Yeah, that works. Is it closed under scalar multiplication?
Yes.
No.
Aren't you
No.
restricted?
Where do my scalars come from?
Oh, they come from R.
They don't come from the subset I'm pointing at. They come from the field of the original guy. So I'm thinking of R, and of course here I'm talking about over R. Right? R is usually going to be the field. So it turns out it's closed under addition, but it's not closed under scalar multiplication. This does not satisfy our properties of a subspace. That's not one of them.
Like R itself.
And for the same reason, the set of irrationals won't work, right? Because it's possible, give me a rational, give me an irrational, I can multiply it by a scalar to make it rational. But yeah, R itself would be one. Of course, it's a vector space, and every set is a subset of itself, so that works. What else?
The zero set.
The zero subspace. The set containing only the number zero. Remember, this falls under the zero subspace that I mentioned before, called the trivial subspace. What else?
R2, R3.
Well, R2 is not a subset of that. Are there any more for R?
How about 0, 1? No, no.
No, 0, 1, 1. Because I can multiply by a scalar and not get 0.
Oh, yeah, true.
What if you do something like cyclic? Like modulo something. Like R, like a segment, like a finite segment modulo something.
You're changing this though.
Oh,
So, but even if you take subset, the modular subsets of that, like all the guys that are equivalent to 1 mod 3 or something like that you're talking about, you can still kill those because those guys would sort of focus only on integers and you can multiply by a real number and mess everything up. Turns out that's it. There are only two. There are only two subspaces of R. Maybe if we go up a notch, that will change. So let's look at R2. R2 itself is clearly a subspace of itself, and the zero vector, in this case, that means this element specifically, namely. Those two are subspaces. Who else can you think is a subspace?
well, R.
Hmm?
R, R1.
Well, how would you describe that in this context, though?
Like the set of x's and y, like where so like x or where y is a fixed number or something like that. Like just a line within the plane,
A line within the plane.
a horizontal line.
So this. Say I picked
Well,
y.
that doesn't have this zero, so that'd have to
That
be
doesn't.
the axis, the x-axis.
So the x-axis itself would contain the zero, right? So what would points on that line look like in R2? These would be guys that look like
X comma zero.
x comma 0, and that there's another guy that might look like a comma 0. Now if I add two of those guys, I get someone that looks like those guys. If I multiply any of those guys by a scalar, I get someone that looks like those guys. So that's a subspace, right? It turns out if I look at guys that look like x comma 3, that's no longer true. If I add two guys that look like that, the y component becomes 6. So that's going to mess up the form. I'll exit the set. So yes, the x-axis is one such line. Any other lines?
Y-axis.
The y-axis will also work. What else?
X equals y,
We're seeing a pattern here.
x equals minus y.
X equals minus y, yeah.
It's art. Any line that contains the origin?
Any line through the origin. Now, is there any other class? What about other kind of objects that pass through the origin? What about looking at like a parabola? That contains the zero vector. Right, looking at all points that look like x comma x squared. Vector space?
Multiplying by a scalar won't guarantee the square, right? Let's say that you choose a number and...
Yeah, and also addition doesn't work either, right? So if you take two guys that looks like that, a and a squared, then you add them, you get x plus a, comma, x squared plus a squared. But this is not the same as saying x plus a, but you want this component squared, right? Because the square of a sum is not the sum of the squares. These guys won't have the right form, and that's not going to work. Right? So once you have a power, it seems to suggest, once you have a power that's not 1, you're going to kind of break this because powers don't distribute across sums, which you know from arithmetic. Right? So it turns out that lines through the origin are the only other class of things that will be subspaces. So in R2, there are only 3 kinds of subspaces. You can have the entire set itself, the trivial subspace, or any line through the origin. Those will be the only ones. Lines that don't pass through the origin, they will fail because axiom 4 will not hold. They will not contain a zero vector. But otherwise, lines through the origin, they will hold. Because lines through the origin, what would they look like, lines through the origin? Yeah?
I was just gonna ask, does that count as infinitely many objects at every single line through the origin, or is that just a reflection of, or a rotation of one line?
It depends on the context, but for us we can think of it as an infinite number of objects. I think to think of it as just one thing, you'll be thinking in terms of something larger, like a category or something. Yeah, what about R3? What do you think?
Sorry, so going back, so would R just fall into the class of any line through the origin?
Yeah, like if you're in R, if you're in the real line, you only have one dimension. Any line passing through the origin
Okay.
is literally all of
Okay,
R
so you don't have to
itself.
specify that.
So you wouldn't have to specify that. Specifying that is saying this. So it turns out this infinite number of cases in R2 collapses to a single case in R, which happens to be R itself. What about R3? What do we think? Well, R3 itself, sure. The 0, sure. What else? Lines through the origin, of course, sure.
Planes through the origin.
Planes through the origin. Would be another category. They contain the zero vector. They don't have any power, they don't have any elements with powers other than 1 or 0, so they're not going to mess up the addition or scalar multiplication. Okay. So now we're at Rn. What do you think? How many different classes of subspaces will we have in this case? Of course, there's Rn itself. There's the 0.
N plus 1?
N plus 1 what?
I'm sorry, like when you asked the question, like how many?
Yeah.
N plus 1 being the number
Oh,
of.
everything.
How many classes? Okay, but tell me what would they look like?
You build up to it. Next one,
So you'd have lines through the origin, planes through the origin,
40, whatever.
4D planes through the origin, 5D planes through the origin, 6D planes through the origin, until you hit whatever n is, right? So there will be a whole list here, and this list will contain n-dimensional hyperplanes through the origin. So the one-dimensional hyperplane through the origin is just a line. The two-dimensional hyperplane through the origin is just a typical plane that you can draw in Calc 3. But higher than that, we just have higher dimensional planes. So you can actually separate them by dimensions. These are all the classes of subspace that are possible, with the usual operations, that is. And that will all there could ever be. Right, so no matter what kind of description you put on things, your subspace will have to fall into one of these categories. You don't have infinite variety. So and this is again something we'll come back to when we're talking about linear transformations. Remember those two arbitrary rules I spoke about? How if this is a function, I want to be able to add two things and then it be this. Right, I made that arbitrary distinction. That's because I want to maintain this idea that I can combine things and not worry about exiting the property that I care about. Right, I can still maintain its vector space property if I require this. So if t was a function that squared things, I cannot say the square of a sum is the sum of the squares, right? But I want to be able to say that. So this is kind of a property I would care about, and this is one of the reasons why I mentioned we're going to talk about functions, yes, and we care about functions in general, but right now specifically we care about functions that have this property. And it's because I want to maintain closure under addition. And the other property I told you about those functions is I want to maintain this being true all the time, because I want to maintain closure under scalar multiplication. Because I know if I maintain those two, I maintain all the vector space properties. So once my function can have these two things, that theorem, ultimately when we pull it back to the theorem, it's going to be able to tell us, yeah, if our function has these two things, we're not screwing up the fact that we're working on vector spaces here. So if we can connect two sets with such a function, they have to be vector spaces. You will never be able to screw it up and connect this thing to something that's not a vector space itself. That's much later, but I just wanted to get into. So the important thing is know how to check for what a subspace is and understand that how the details will vary depending on the kind of objects you're looking at. So you have to first of all know what form your objects come in and make sure that when you're picking, if you have to pick arbitrary things, you're picking the arbitrary things that satisfy the property. What else do I want to talk about? Okay, we mentioned these as vector spaces. You've seen all these before. I'm going to tell you how they relate to each other. I mean, we mentioned them already. So we can look at this little guy here, Pn. Set of all polynomials of degree n or less, those guys formed a vector space. We kind of already justified that. Turns out that these are just one small part of a class of functions that are the C infinities. These are the infinitely differential continuous functions, and polynomials are just one such kind of continuous function. Outside of those, you'll have the Cn's. Right? These are the n differentiable classes of functions. It'll go all the way down like Cn minus 1, And there's an infinite number of things in this group, by the way. But it will go all the way down to things that are only once differentiable. That is contained in the set of all possible things that are just continuous with no requirement on differentiability. That is contained in f of infinity, which is just a set of all functions. So things can get bigger and they relate to each other in this kind of way. Turns out if I'm talking about in calculus, this would be the order of things. Polynomials are a very special class, a highly selective group. Right? And so, in other words, this is also, among other things, another reason why Taylor series were so useful, is that we can, if we can get all of these guys to just behave like that little guy, that gives us a lot of power, right? If I can somehow write all of these guys to look like guys over there, like polynomials, then only knowing this much knowledge can kind of apply this far. And that's very useful. What else do I want to mention?
Professor,
Yeah.
could you contain all of that within C, the complex numbers, or like the last? Like, could you add an extra like circle? Or is that like everything?
But what, in what context? If I'm gonna throw in C, I would probably put him in here.
Oh, I meant with the imaginary like, complex numbers.
Yeah, but how does that relate to functions?
Could you have like complex functions with like an
Yeah, you can have complex value functions, sure. But I would do this instead.
okay.
C would be the domain is what you're talking.
Okay.
Here's something I also mentioned before. Like, the solution set to Ax equals 0 is a subspace of the domain. Is a subspace of the domain space, right? So if I'm looking at all these variables, the possible domain, like if I'm thinking of, oh, these components have to all be real numbers, then the guys that solve the set that these guys would come from, so let's say it's in Rn, say example, let's say A is n by n, then Rn could be a domain. Right? So if A sum n by n matrix and I form this equation, and I'm only taking the vectors out of this set that solve that equation, it turns out that those solutions form a subset, a subspace. You can prove this. Closure under addition. How would you show that? The x and y be solutions to ax equals 0, or let a and b, or something like that. What can we say here?
Cases? Do you have to see like if it has like one solution or infinite many? Like, no
Well, what is the form? How do I know it's a solution? What form must it take?
It's
Or how do I, what's the classification? How do I know something is a solution to that equation?
using the components of X as weights, a linear combination of the column vectors of A. It's basically the matrix, right? You have to set up the, we'll give you back.
So set up a random matrix? How do I know that random matrix is a solution? Like sure, you want me to say that A looks like this, which you probably shouldn't assume anyway. Okay, how does that tell me it's a solution?
A times that gives you back the zero vector in your space.
Okay, so that's what it means. To be a solution means when I plug it into this equation, it's true, right? So to assume these are solutions, then that means if I take A and multiply by this vector, I get the zero vector. And if I take A and multiply by this vector, I get the zero vector. which means, is the sum a solution? So I know each individual is a solution. I want to know, does the sum of them belong to the set of solutions?
You can right distribute.
You can right distribute A by the matrix properties. I know that this gives me 0 by assumption. 0 plus 0 gives me 0 by definition of the 0 vector. This means A plus B is a solution. And that gives us closure. Okay. So again, we're verifying closure under addition. It's not so much that these guys can look a certain way, but it's that they perform a certain property. They are the guys when I plug into this equation, I get 0. And so if I know individuals solve that, I need to know, do their sum solve it? What about scalar multiplication?
Professor, I have a question.
Yeah.
So could we also like add those two vectors in terms of components, so you're back in the reals, and then treat that sum as a m by 1, and then do that same thing? Would that work too? So I think that's like in matrix form, right? So
Yeah, but I want you to get away from thinking about it that way because it might not be Rn.
what do you mean?
Like our vectors here, they might not live in Rn. Rn doesn't have to be my domain. I say it could be the domain. There are a multitude of things that I could express like this. I can express a linear homogeneous differential equation in this form. Right? I can express a system of linear homogeneous differential equations in this form, where my a's, they aren't components of Rn, they're actually differentiable functions. So the moment you kind of say, I can write them as components and add component-wise, you're putting yourself in a box that was not assumed. Right? But here, this doesn't matter what they look like because I know this property holds. We've proven that. And under scalar multiplication, if A is a solution and K is any scalar, then if I take A times the scalar times A, that would be equal to what?
It should equal to 0 vector.
Well, I can factor that out, and that's also from properties of matrices.
0.
And so this part here I know is 0, so that's k times 0, but we've proven that in a vector space, k times the 0 vector will be equal to 0. So it's closed under addition, and that's a subspace. Now this is a very important subspace. In fact, there are many things that we can express in this way. This is a very important subspace. So important, meaning the solutions, i.e. the solution space to a homogeneous system. It is called, we give it a name, the null space of A. Or, and this is in the future, this is what we call it more. If we're thinking strictly, usually we use this phrasing if we're thinking of A strictly as a linear transformation. So it's a null space of A. Here we're basically thinking of A as a matrix. right, then the common vernacular is to say, oh, it's the null space. If you're thinking of A as something else, if you're thinking of A as a function, then we call it the kernel. And this is a much broader definition because it will apply even in non-vector space cases. We can talk about the kernels of homomorphisms, the kernels of groups, or other, not kernels of groups, but a lot of other things. So this is kernel of A. This is if we're more thinking in terms of functions. That will be the more used version. But either one. So if someone talks about the null space or the kernel, they're talking about specifically the solution to a homogeneous equation.
So the kernel, are you saying the function, which is the solution to a equation? Just to think about what that means, because the null space is like, what does it mean to be the kernel of A? Like, as the thing that solves the function.
Yeah, the thing that solves it. So if
Okay.
I say the null space, there'll be another way to interpret null spaces in terms of matrices. So let me probably just define the kernel this way. The kernel of A equals the ker, that's the notation. It is going to be the set of all x in the domain such that it solves this equation. So it's just it's a set of inputs, right? And we call them the kernel. And there are many things we know of as the kernel. And thinking of a lot of things as kernels allows us to solve a lot of other problems. So in other words, like even in a broader context, we can think of, not a broader context, but something I mentioned before, you're back in differential equations solving homogeneous linear systems, you can think of any solution to that system as a member of the kernel of some equation like this. So the solutions to linear differential equations are just the kernels of some matrix. Now if you're not zero, there is a theorem in differential equation that says your solution must look like the members of a kernel with arbitrary scalars in front of it, plus some particular solution that you can choose at will. And we're actually going to prove that theorem in this class. Like why that is, it's a consequence of linear algebra. And we're going to prove it. Yeah.
If we think of A as a function, then x is like the input to that function, right? Not,
Yes.
It's not multiplied by. Okay.
Technically, it is multiplication, but that's you think of it as input. You can think of it as
Okay.
it's going to be weird when we start talking about linear transformations, which is pretty much the end of chapter 4, like in section 4.10 or so. We're going to get back to that. It turns out that I can describe the output of a function. If I can describe the matrix as a function, I can describe the output via matrix multiplication. So yes, on one hand, you're thinking of it as plugging into a function, but on the other hand, it turns out to be equivalent to just multiplying it by the matrix. You'll get the same outputs, no matter which way you think about it. So that's kind of neat. That's kind of why we like this linear algebra thing. It makes things a lot easier. Don't just plug things in, it's just a matrix multiplication. Okay, what else? Okay, so those are just a few examples about working with subspaces. Let's take some time and go over some definitions, and we'll come back to this. So it's just a foreshadowing. So let's look at some theorems, definitions. That will come in handy later. Theorem. First one. We have a finite list of subspaces of a vector space, then their intersections of subspace. Let V be a vector space, and let W1, W2, Wn be subspaces of V. then the intersection of all these subspaces. So I goes from 1 up to n wi. That's just basically me saying w1 intersect with w2 intersect all the way down intersecting with wn is a subspace as well. The intersection of subspaces is a subspace. Proof. Left to the reader. But it's not that bad. Again, you'll prove it exactly the same way. Let A and B be two elements in this set, which means they're elements of this set, which means they're elements of every single one, right? So that means if A and B is a member of W1, then W1 is a subspace. So if I add them, I get a member of W1. But that's true for everyone, so it's true for the entire thing, because we're taking intersections. And then you can do the same kind of argument with scalar multiplications. Because the two guys that you pick are in the set ends up being members of literally everybody, but because everybody is a subspace, adding them is also a member of everybody. And so if the sum is a member of everybody, it's a member of the intersection. And you can do the same thing with scalar multiplication. So that's not so bad. There's another theorem. I want to define a linear combination. V1, V2, Vn, and V. And C1, C2, Cn, and F. Of course, where V is a vector space over F. We call this element I'm going to define C1 V1 plus C2 V2 plus Cn Vn. A linear combination of the vectors v1 through vn. So this kind of expression, we will call it a linear combination. It's a super important kind of expression. Ultimately, at the end of the day, we are going to be able to prove that any n-dimensional vector space is isomorphic to Rn. Meaning, if I find any vector space of a finite dimension, I can think of it as being exactly the same as Rn. They're the same. You just might change the names, you might change what they look like, you might change what you call them, how you treat them. But essentially, guys that corresponded in Rn will correspond in this new context, and they'll all play together in exactly the same way, and it's predictable. And the way you prove that is to actually focus on the coefficients, right? If your CNs come from R, you can uniquely identify any vector with those Cs. And those C's you can put in a vector, and that vector will live in Rn. And so we can uniquely identify any random vector in our vector space with a coordinate in Rn, and the link will obey all the properties that we need it to obey. But again, getting ahead of myself. I get bored writing down definitions, so sometimes I'll just ramble. Okay, so I need to say what a linear combination is. And by the way, that WB, the set of all possible linear combinations of V1 to Vn. Then it turns out W is a subspace subspace of V that contains these vectors. We'll soon be concerning ourselves with redundancy. So if we have something that fulfills a certain property, we're going to want to find the smallest guy that fulfills this property, because the extra information can be problematic. It's problematic also because of certain things we want to verify, that whether functions are one-to-one or onto. If something has several outputs, it's kind of problematic. We need only one, some sort of uniqueness. So we need to cut off all the fat, make sure that we're as small and as tight as possible, and everything is minimally done. No waste of information. So oftentimes knowing what's the smallest thing that fulfills a property is going to be useful for us. So it turns out that if I have a set of vectors here, and I want what is the smallest subset of my vector space that contains those vectors, it turns out the set of all possible linear combinations is that set. So basically, first you have to prove that this is a subspace, which you can just show that if I can add two guys of this form and I'll get a guy of that form. If I multiply this by a scalar, I will get a guy of this form, so it's a subspace. Then you show that assuming there's some other subspace that contains these, it must contain this as well. Right? So if I assume that R is some other subspace that contains these vectors, because it's a subspace, it must contain any scalar multiple of these vectors. And then it must also contain the sums of all these scalar multiples of those vectors. Therefore, it must contain things that look like this, which means it contains W. Okay. What else? And here, of course, my X lives in V. Just by how a vector space is constructed, multiplying everyone by a scalar, I stay in V. If I add two things in V, I stay in V. So it turns out a linear combination of vectors in V is also some other element of V. Now, if we can write X equals C1 V1 plus C2 V2 plus Cn Vn, and we fix the so this is kind of getting to the notion of an ordered basis we will talk about. So I don't want a rearrangement of these things, guys. Even though sums, I know they're commutative, but I want V1 to always represent a particular guy. V2 always represents a particular guy, so I don't want this to change based on rearrangement. So let's say I fix the identities of the VI's, and I can express some element in terms of this thing. Then we can say a bunch of things. One, we can say X is in the span of the set V1 through Vn. And we can say the vector C1, C2, Cn. Notice that guy would live in Rn, assuming my field is the real numbers. Is called the coordinates X. So, example. Set V equals R2. Set the vector V1 to be your I vector. Set the vector V2 to be your J vector. And let X any vector A, B in R2, then we can write AI plus BJ in order to accomplish this guy here. And so usually when we talk about coordinates, we're thinking of pairs, but for our purposes, we'll also start to think of this as just a linear combination of certain vectors that can span enough elements that we like. So this guy is what we call the coordinate. And it's the coordinate with respect to I and j. Now a lot of us kind of always think of these, we always think in terms of I and j, but we want to sort of get away from that. I will give you another set of coordinates that can do the same thing that I and j will do, and it will give you coordinates that look different. So, here it comes. Kind of jumping ahead, but I feel like it's nice to do it here. Here's another example. Again, set B equals R2 with usual operations. Take my V1 to be this vector, 1, 1. To my V2 to be this vector, minus 1, 2. And here's the question. What is the coordinate of the vector AB with respect to these guys? How would you go about answering that question? Yeah?
You could do V1 plus V2 1. You could add them across if you do.
So this means I want to add them. So AB I want to be able to write as C1 V1 plus C2 V2, right?
Right.
I want to be able to express that as a linear combination of these guys. So what I need to be able to do is to actually find these coordinates. How would I go about finding such coordinates? Let's start by replacing them. V1 is 1, 1. V2 is minus 1, 2.
It's a system of equations.
It's a system of equations. Why, look at that. Luckily, we did chapter 1, so we know how to deal with this. So somehow, I want to change the important guys I'm expressing people in terms of, and I want to be able to write things in terms of different coordinates to locate them differently or figure out something in a different context. It turns out that in a vector space, it kind of ends up being the solution to some system of equations. But let's actually continue here so you can kind of see what this will look like, and then I'll point out a specific example. So basically this is saying that your AB is going to be equal to C1 minus C2 and C1 plus 2C2. Or in other words, I can think of this as 1 minus 1, 1, 2 times C1, C2. So this ends up being a system of equations. So answering the question, how can I write coordinates in terms of these two new vectors? It ends up being the solution to a system of equations. So what we would do is we augment these guys, and let's actually go through the process. So we can have 1 minus 1a, let's leave that. I'm going to get to reducer echelon form. I want to kill that guy, so I'm just going to subtract. 0. Let's do row 2 minus row 1. This minus this minus that. 3 is b minus a. So I can now do something like row 1 times 3 and then add them. So I get 3, 0, and b minus 2a plus 2a. Because I'm adding them. It's row 1 plus row 2. And this would be 0, 1, b minus a over 3. And so I will end up with 1, 0, 2a plus b all over 3, and 0, 1, b minus a over 3. i.e., AB, in the usual way we think of it in R2, can be expressed as the coordinate 2a plus b over 3, b minus a over 3, with respect to v1 and v2. So looking at this guy, I'm going to think of this guy when I want to work in this context. It's kind of like when you're doing Calc 2 and you're over a region where things are in terms of a circle. Sometimes it was convenient not to think of things in terms of x and y, but to rather think of them in terms of r and theta, right? So you literally change the entire way you look at the world, the entire way you locate something, and it ends up making the problem easier to solve. In the same way, that's kind of what coordinates are doing. Coordinates are our addresses. It's how we would locate some element in our vector space. So somehow we want to be able to spread out a vector space in some intelligible way, be able to write the address for everyone in that space, and sometimes I might want to require that that address takes certain important factors into consideration. And I might already know an address that takes a lot of important factors into consideration. Pretty much the Cartesian system, the consideration was how can we do this as easy as possible, right? Where the coordinate is literally the same as the scalars in front of the vectors. You get the Cartesian coordinate system, but you might want to look at the world in a different way, and that will change where all your how your coordinates look. And that can help you to solve new problems. It'll literally kind of change your world without making anything too different, but making them different enough to be able to solve a certain problem that you care about.
Well,
Yeah.
did you not just solve for C1 and C2, not A and B? If you have A equals 2A plus B over 3, and B equals B minus A over 3, and that.
No, what I'm saying is that the AB what I'm saying is here is that AB is equal to 2A plus B over 3 times the V1 plus the B minus A over 3 times the V2. Now at the moment I don't really have a notation.
It's in like a different frame of reference.
Yeah, in this case I don't want you to think of this as being the same as that, even though,
Okay.
It's notation I will do later, but for example, what we can do is we can say, oh,
I mean, can't you just call the thing C1, comma C2?
so I can take my two vectors and throw in a set. And how I would identify what my frame of reference is I would put the name of that set as a little subscript. It's kind of like how if you're doing things, if you're using counting numbers but you're in base 2, right? So when you write down the number 1011, if everyone understood, yeah, we're in base 2, that's cool, but if someone might not know, you can put a little 2 here.
I'm just
Right.
confused why we're using the same variable on the left side and the right side.
Well, it won't be the same. Like if this is A, that's gonna be something else.
But A appears as like.
Yeah, because it's related to A in some way. You know, what you can think of is me changing the coordinates is something that's going to link what this guy was with respect to the old address to what that guy is with respect to the new address. They're the same guy. I just
Same
think
point in space, or, I mean.
it
maybe
won't be the
that's not
same
a good
point in space in R2.
Point on the plane. I mean,
Is it better to think of a point in the world of those two vectors, v1 and
So
v2?
like, for example, like if I said AB was the vector 1, 2, that's the location I know in the usual Cartesian system,
yeah.
right? Then, with respect to the new coordinates, right, if I look at 1, 2, I could write that as a new coordinate. And what would be the elements of that coordinate? Well, it's going to be 2 times this plus that, which is 4 divided by 3. And it's going to be 2 minus 1 over 3. Right? So this is this new thing in this new coordinate system. So this guy would now go to, well, that guy.
Wait, but isn't it saying 4/3 of that different, I mean, different vector plus 1/3 of the other different vector, like the B?
Yeah, this is actually
Set.
4/3 times
Doesn't it correspond to the same
1,
point?
1 plus 1/3 times, what was the other guy we had? Minus 1, 2. Yeah, I'm saying that I can express this vector in the usual way I'm used to thinking about it, as this way.
Yeah.
When expressed in it, when I'm thinking of it in terms of this way, use that notation.
So it actually lands somewhere else.
No, we're talking about the same point, just in a different basis.
That third thing's a dot product, right? And then the second thing's like the components. I mean, the actual vector itself with the components.
Maybe this might answer the question. Because we're superimposing, I think the reason why you're confusing is because we're superimposing the new world on top of the old world. But maybe this might help you. In Calc 2, we do something called rotation of axes. You did Calc 2 here? Yeah. So in Calc 2, we did something called rotation of axes, right? So there's this idea that, okay, there's an object called an ellipse, right? And this is going to be its equation, right? It's going to be x minus a squared over x minus a squared over a squared plus I minus k squared over b squared equals 1, right? And this is what I'm thinking of it in the usual coordinate system, right? That's what an ellipse looks like. But things can be degenerated. You can have something that's an ellipse, but you'd never be able to recognize it as an ellipse because it's shifted. It turns out that if you find the equation of something like this, it will not look like that. So in other words, what they did was what's called a rotation of axes. You kind of showed that there is some angle that I can rotate by to say that, you know what, it's the same guy. Sure, this point here might correspond to some other point here, but it's the same guy. He's in the same position in this new frame of reference. He will perform the same functions in the new frame of reference that he did in the old frame of reference. Now their locations might appear to change, they might appear to look different, but they're the same guy. So I can say, make a connection between all different points. So technically, because we're still looking at this as the x and y plane, so you're not going to see it. But if we looked in this new plane, x prime, y prime, we'll see exactly the same guy. He's in exactly the same position he's in this new universe. But it's kind of confusing when I just put this on top of the old universe, right? It might look like he's changing position, but actually nothing is really changing. I'm literally just tilting my head and thinking of the axes as going this way as opposed to the other way. And when I do that, the formulas will look different here, but when I make the correction, the formula here in this new universe will be in terms of x prime minus h squared, blah, blah, blah. Everything will start to look familiar, but I have to go through this change where the guy seems to look different, but really he's performing the same function, same position, it's just a different frame of reference. Right. We'll talk about this later. What I'm talking about here is called a change of basis. It turns out that the two vectors I mentioned earlier was a basis for R2. So they were linearly independent and they spanned the set, and it allowed us to do this kind of manipulation. But that's kind of where it's going to go. And coordinates are one way that help us get there. Being able to express something as a linear combination allows us to look at coordinates differently, in such a way that they're different, they look different now, but if I change the frame of reference, they do exactly the same thing I wanted them to do from the beginning. It's just that as it was presented to me, it wasn't useful. So I had to somehow change things, shift things, use a new coordinate system to make it now useful again. Right? I know how to deal with that, I don't know how to deal with this, but really this is just that in a different frame of reference. Right? So yeah, the numbers are going to be different, and if you're plotting things on top of the same background, it'll look like things change position, but the point is, this position is in a different universe. You know, it's like in those shows where someone slips off into a different dimension and they're walking on. Like Doctor Strange, you saw Doctor Strange? Like it's, oh, you haven't seen Doctor Strange? Yeah, that's your homework. Oh, yeah. Yeah, so that's kind of the idea. So the coordinates is just a different way of locating things, but it's going to keep all the same essences. So it is going to have some relationship to the original. You should expect to find the same if you represent this as an AB over here, you'd expect to find something to do with AB over here, because you're really making a connection to the same guy. But somehow, him in this environment is not as good as me thinking of him in another environment, with another address and another set of locations. But again, we're getting ahead of ourselves. Because we're really like, that's like 4 sections from now we're going to talk about that. So that's the idea of a coordinate. So we can have a bunch of vectors in a vector space. We can create linear combinations. And if we order the vectors that we're making the linear combination with, and only look at the scalars that are in front of them, we can create coordinates that live in our field. And then we can play around with these coordinates and change them at will to accomplish some purpose without changing the properties of the original, of how they behave in the original vector space. Okay, so let's broaden our definition of span right now. So let V be a vector space. We say V1, V2, Vn spans V if for every element in V we can express it as a linear combination of these vectors. And in that case, we say that these vectors span this set. So that's what it means to span something.
Do they have to be in the vector space, those vectors?
Yes.
Is it necessary? Okay.
Yes. And the fact that this is also an element of the vector space is clear from the definition of what a vector space is. It must contain scalar multiples and sums. So this is clearly also a thing in a vector space, but what makes the span the important thing is that literally anything I can write in terms of this, in this way, with these particular vectors. And that's not always the case. And I can give you an example. I and j span R2. In fact, since any xy in R2 can be written as that vector is just some scalar times I plus some scalar times j, where x, y are in R. It's also true that these two new vectors I told you, v1, which is 1, 1, and v2, which is minus 1, 2, also span R2, right? Since for any xy in R2, we can write xy would be equal to, what was it, 2x plus y over 3 times this vector plus, and this is a scalar, this is like a C1, plus, I think it was y minus x over 3 times that vector. So these guys are called span. And in this context, the sets ij and 1, 1 minus 1, 2 are called spanning sets. You can note, in general, given V, spanning sets are not unique. In fact, let's even just for R2, there's an infinite number of vectors that I could choose that can span them. I can write coordinates in an infinite number of ways. But it's not at all random. It is possible to take two vectors and then not span the set. In R2, it'll look kind of stupid. It will be obvious. But in R3, we'll start to see more examples, which we'll probably do next. Another thing that we can say, just in case you hear it, And in this case, we could say B is generated so that's the terminology that we use by its spanning set. So example, you could say the phrase R2 is generated by I and J.
Does that mean R infinity doesn't have a spanning set?
R infinity does have a spanning set. It just happens to be an infinite set as well. But we'll continue next time. We'll do a few more examples. We'll define linear independence, and then we can talk about bases. As well as I'll give you some examples in R3 as well, because if I give you examples of this in R2, it's going to look stupid. So, you can do that. Remember, tomorrow we have our test, and that's it. Any questions? See you guys tomorrow.